Welcome to Sleepy Science Hub. I'm so glad you found your way here tonight, to this peaceful space where the mysteries of quantum physics meet the gentle art of restful learning. As you settle into your most comfortable position, wherever you might be in the world right now, take a moment to let me know in the comments where you are and what time it is as you listen. There's something wonderfully soothing about knowing we're sharing this quiet moment of discovery together, connected across space and time by our curiosity about one of the universe's most beautiful and mysterious phenomena. Tonight, we're going to explore something that sounds almost magical: the Quantum Zeno Effect. With a simple act of gentle observation can literally freeze time at the quantum level. But don't worry about complex equations or intimidating physics concepts. We're approaching this remarkable phenomenon like peaceful observers in a quantum garden, where watching becomes a form of meditation, and understanding unfolds as naturally as morning light spreading across still water. Now, get comfortable. Adjust your pillows, pull your blankets close, and let your breathing settle into its natural, peaceful rhythm. Take a slow, deep breath, feel your body releasing the tensions of the day, and let's begin this tranquil journey into the quantum realm where time itself can be gently coaxed to stand still. As you lie there in comfort, your breathing gradually slowing and deepening like the gentle tide of quantum waves that flow through all matter. Imagine yourself walking through a garden unlike any other, a place where the ordinary rules of everyday experience give way to something far more mysterious and beautiful. This is the quantum garden, a realm that exists all around us and within us, yet remains invisible to our everyday senses, operating according to principles so gentle and subtle that they seem more like poetry than physics. In this quantum garden, particles dance to rhythms that exist outside of classical time, where the mere act of watching can change the nature of reality itself. Here, observation becomes a creative act, a gentle touch that shapes the world through the simple presence of attention. The Quantum Zeno Effect that we'll explore together is perhaps the most beautiful expression of this principle. The discovery that frequent, gentle observation can literally prevent quantum systems from changing, freezing them in time like delicate flowers preserved in the amber of consciousness. Picture yourself settling onto a comfortable bench in this quantum garden, surrounded by phenomena that would seem impossible in the everyday world, yet represent the fundamental nature of reality at its most basic level. The air around you shimmers with invisible probability waves, each one carrying the potential for countless different outcomes that exist simultaneously until the moment of gentle observation collapses them into a single, definite reality. These waves don't crash or thunder like ocean waves, but flow with the peaceful persistence of morning mist, carrying information and possibility through dimensions that exist beyond ordinary space and time. The quantum realm operates on principles that initially seem counterintuitive to our everyday experience, yet make perfect sense when approached with the patient curiosity of a child exploring a new playground. In our ordinary world, objects have definite positions and move along predictable paths. A ball thrown across a room follows a clear trajectory from point A to point B. But in the quantum garden, particles exist in multiple places simultaneously, following all possible paths at once until the gentle act of measurement causes them to choose just one reality from the infinite garden of possibilities. As your consciousness settles into harmony with these quantum rhythms, your breathing becoming as measured and peaceful as the oscillations of elementary particles, you begin to understand that the quantum world is not chaotic or random, but follows its own elegant logic based on probability, superposition, and the profound role of observation in shaping reality. The mathematics that describe these phenomena are beautiful in their symmetry and precision, but you don't need to understand equations to appreciate the deeper poetry of quantum mechanics. The way it reveals a universe that is participatory rather than purely objective, where consciousness and reality dance together in an eternal quantum waltz. The history of quantum mechanics reads like a story of gradual awakening to the true nature of reality. In the early 20th century, scientists studying the behavior of light and matter began to notice phenomena that couldn't be explained by classical physics. Light sometimes behaved like waves and sometimes like particles. Electrons seemed to orbit atomic nuclei in ways that defied conventional understanding. Energy appeared to come in discrete packets rather than flowing continuously. These discoveries didn't come through dramatic breakthroughs, but through patient observation and careful measurement, each experiment revealing another layer of quantum mystery. The pioneers of quantum mechanics, scientists like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg, found themselves grappling with concepts that challenged their most basic assumptions about the nature of reality. They discovered that at the quantum level, the act of measurement doesn't just reveal pre-existing properties, but actually creates them. Before measurement, quantum particles exist in superposition states where they embody multiple contradictory properties simultaneously. A particle can be spinning clockwise and counterclockwise at the same time, or exist in multiple locations simultaneously, until the gentle intervention of observation forces it to choose just one possibility. This relationship between observation and reality forms the heart of the Quantum Zeno Effect, named after the ancient Greek philosopher Zeno of Elea, who proposed paradoxes about motion and time that seemed to prove movement was impossible. The Quantum Zeno Effect demonstrates that frequent observation can indeed freeze quantum motion, not through philosophical argument, but through the actual physics of quantum measurement. When we observe a quantum system frequently enough, we can prevent it from evolving, keeping it frozen in its initial state like a photograph that captures a single moment and holds it eternal. The beauty of the Quantum Zeno Effect lies not in its practical applications, though these are numerous and important, but in what it reveals about the fundamental nature of reality. It shows us that the universe is not a mechanical clockwork operating independently of consciousness, but rather a participatory creation where observation plays a crucial role in determining what becomes real. This doesn't mean that reality is purely subjective or that we can change the world simply by wishing, but rather that consciousness and the physical world are more intimately connected than classical physics ever imagined. In the quantum garden where we find ourselves, time itself becomes fluid and malleable. Classical time flows like a river, carrying all things forward in a steady, unstoppable current. But quantum time is more like a still pond, where ripples of possibility spread outward from each moment of observation. When we watch a quantum system frequently enough, we can effectively stop these ripples, freezing the system in a timeless state where change becomes impossible. This is not the violent freezing of winter ice, but the gentle preservation of a perfect moment, like the way meditation can make a single breath feel eternal. The philosophical implications of the Quantum Zeno Effect extend far beyond physics into questions about the nature of consciousness, free will, and the structure of reality itself. If observation can freeze quantum evolution, what does this tell us about the role of consciousness in the universe? If reality is partially created through the act of measurement, how do we understand the relationship between mind and matter? These questions don't have simple answers, but they open doorways to deeper understanding of our place in the cosmic order. The experimental verification of the Quantum Zeno Effect required extraordinary precision and patience. Scientists had to learn to observe quantum systems so gently that they could detect their evolution while simultaneously preventing that evolution through the very act of observation. This delicate balance between watching and interfering reflects one of the most subtle aspects of quantum mechanics, the recognition that there is no such thing as completely passive observation. Every measurement requires an interaction. Every observation leaves a trace. Every act of watching changes what is being watched. The technical implementation of quantum Zeno experiments involves tools and techniques that operate at the very limits of human precision. Laser beams cooled to temperatures near absolute zero, magnetic fields controlled to within billionths of a Tesla, detection systems capable of registering single photons. All of these technologies work together to create laboratory conditions where the subtle effects of quantum observation can be studied and verified. Yet despite the complexity of the experimental apparatus, the underlying principle remains beautifully simple. Watch something quantum mechanical frequently enough, and you can prevent it from changing. The atoms and particles that participate in quantum Zeno experiments don't experience this freezing as constraint or imprisonment. From their quantum perspective, being held in superposition by frequent observation is as natural as floating in a weightless environment. They continue to exist in their full quantum glory, embodying multiple possibilities simultaneously, simply prevented from collapsing into a single classical state by the gentle touch of repeated measurement. As you continue to rest in this quantum garden, your breathing now completely synchronized with the timeless rhythms of quantum mechanics, you can begin to appreciate how the Quantum Zeno Effect offers a new way of thinking about time and change. In our everyday experience, time seems relentless and unstoppable, carrying us forward whether we're ready or not. But the quantum realm reveals that time is more flexible than we imagined, that moments can be stretched and held, that change can be paused through the simple act of paying attention. The meditation traditions of many cultures have long recognized that focused attention can create experiences of timelessness, where hours can pass like minutes or single moments can feel eternal. The Quantum Zeno Effect provides a scientific parallel to these contemplative insights, showing that at the most fundamental level of reality, consciousness and time are indeed intimately connected. When we observe quantum systems with sufficient frequency and precision, we can literally stop their internal clocks, creating islands of stability in the flowing river of quantum change. The practical applications of the Quantum Zeno Effect are already beginning to transform technology in subtle but important ways. Quantum computers use Zeno-like techniques to protect delicate quantum information from environmental interference. Atomic clocks employ similar principles to maintain extraordinary precision over long periods. Even the GPS satellites that guide us through our daily travels rely on quantum effects that are closely related to the principles underlying the Quantum Zeno Effect. But perhaps the most profound application of understanding the Quantum Zeno Effect lies not in technology, but in developing a deeper appreciation for the role of attention and observation in our daily lives. When we learn that reality at its most fundamental level is shaped by the act of watching, we begin to understand the power of mindful presence, the importance of careful observation, and the creative potential that lies in simply paying attention to the world around us. The quantum garden continues to reveal its secrets to those who approach it with patience and wonder. Every quantum experiment is like tending a delicate flower, requiring just the right touch to reveal its hidden beauty without disturbing its essential nature. The Quantum Zeno Effect represents perhaps the most elegant expression of this delicate relationship between observer and observed, showing us that sometimes the most powerful action is simply to watch with gentle, sustained attention. As your consciousness drifts deeper into harmony with these quantum principles, you can sense the profound peace that comes from understanding our participatory role in the creation of reality. We are not separate from the universe we observe, but integral parts of an ongoing cosmic conversation where consciousness and matter exchange information through the subtle language of quantum measurement. In this conversation, every act of observation is both a question and an answer. Every moment of attention, a gentle vote for which version of reality will manifest from the infinite garden of quantum possibilities. As you settle even deeper into peaceful contemplation, your breathing now flowing like the eternal rhythms that connect ancient wisdom to modern understanding. Let your awareness drift back through time to ancient Greece, where a philosopher named Zeno first glimpsed the mysterious relationship between observation, motion, and the nature of time itself. In the sun-drenched courtyards of Elea, 25 centuries ago, Zeno crafted paradoxes that seemed to prove the impossible, that motion was an illusion, that change was impossible, and that the flowing river of time might actually be a series of frozen moments, each one perfectly still and eternal. Picture yourself walking through those ancient Greek gardens, your footsteps echoing on marble pathways worn smooth by generations of philosophical contemplation. The Mediterranean sun filters through olive trees, creating patterns of light and shadow that dance and shift with each gentle breeze. Here, in this timeless setting, Zeno would gather his students to pose questions that seemed simple on the surface, but revealed profound mysteries about the nature of reality when examined with careful attention. Zeno's most famous paradox, known as the paradox of Achilles and the tortoise, unfolds like a gentle meditation on the infinite divisibility of space and time. Imagine the fleet-footed Achilles racing against a slow tortoise that has been given a head start. Logic suggests that Achilles should easily overtake the tortoise. Yet Zeno's analysis reveals something puzzling. Before Achilles can catch the tortoise, he must first reach the point where the tortoise started. But in the time it takes Achilles to reach that point, the tortoise will have moved slightly ahead. Before Achilles can reach this new position, the tortoise will have advanced again, however slightly. This process continues infinitely, with Achilles always getting closer but never quite catching up, as if trapped in an eternal chase through an infinite series of diminishing intervals. The beauty of this paradox lies not in its logical trickery, but in how it illuminates the profound mystery of continuous motion. When we break any journey into infinitely small steps, each step seems to require its own finite time to complete, suggesting that infinite time will be needed to traverse even the shortest distance. Yet our everyday experience tells us that motion happens smoothly and naturally. This apparent contradiction between mathematical analysis and physical reality opens a doorway to deeper questions about the nature of space, time, and the relationship between our conceptual understanding and the world we experience. As your consciousness settles into the patient rhythms of ancient philosophical inquiry, your breathing becoming as measured and contemplative as the eternal questions that connect Zeno's time to our own, you begin to appreciate how these classical paradoxes anticipated some of the most mysterious aspects of quantum mechanics. Zeno's insight that motion could be understood as a series of static moments finds unexpected resonance in the quantum world, where particles exist in definite states only when observed, and where the continuous evolution of quantum systems can indeed be frozen through the gentle intervention of measurement. The paradox of the arrow provides another window into these timeless mysteries. Zeno observed that at any given instant, a flying arrow occupies a specific position in space and is therefore motionless at that instant. If time consists of a series of instants, and the arrow is motionless at each instant, how can the arrow ever be said to be moving? This paradox suggests that motion might be an emergent property that exists only when we step back and observe the sequence of static moments, rather than something that exists within any individual moment itself. This ancient insight resonates remarkably with modern quantum mechanics, where particles don't have definite trajectories, but exist in superposition states that encompass multiple possible paths simultaneously. The classical notion of a particle following a specific path through space becomes as paradoxical as Zeno's arrow, existing only when we're not looking too closely at any particular moment. When we do observe quantum particles at specific instants, we find them frozen in definite positions, much like Zeno's motionless arrow, with their motion emerging only from the statistical patterns that connect these frozen observations. The resolution of Zeno's paradoxes in classical mathematics involves the beautiful concept of limits and infinite series, showing how infinite sequences of diminishing intervals can sum to finite distances and times. Mathematicians learn to work with infinity not as an impossible quantity, but as a limit that could be approached arbitrarily closely without ever being reached. This mathematical framework allows motion to emerge from the seemingly impossible task of completing infinite journeys, providing a bridge between the static perfection of individual moments and the dynamic flow of continuous change. Yet, even as mathematics resolve the classical paradoxes, quantum mechanics has revealed new depths to Zeno's insights about the relationship between observation and motion. The Quantum Zeno Effect demonstrates that frequent observation really can freeze motion, not through logical paradox, but through the actual physics of quantum measurement. When we observe a quantum system frequently enough, we prevent it from evolving just as surely as if we had solved Zeno's paradox by proving that motion was impossible. The philosophical implications of connecting ancient paradoxes to modern quantum effects extend far beyond academic curiosity. They suggest that human intuition about time and motion, refined through millennia of contemplation, may have grasped essential truths about reality that science is only now beginning to understand fully. The contemplative traditions that arose from Greek philosophy, with their emphasis on the eternal present moment and the illusion of temporal flow, find unexpected scientific validation in quantum mechanics. The modern understanding of space-time, developed through Einstein's relativity theory, adds another layer to these ancient insights about motion and time. Einstein showed that time itself is not absolute but relative, flowing at different rates for different observers depending on their motion and the gravitational fields they experience. This relativistic understanding of time as a flexible dimension rather than a fixed backdrop makes Zeno's paradoxes even more intriguing, suggesting that the nature of time itself might be more mysterious than even the ancient philosophers imagined. The meditation practices that grew out of Greek philosophical traditions often focus on the direct experience of the present moment, seeking to step outside the flowing stream of time and rest in the eternal now. These contemplative techniques bear a striking resemblance to the experimental protocols used to demonstrate the Quantum Zeno Effect, where frequent, gentle observations hold quantum systems in timeless suspension. Both approaches suggest that consciousness has a special relationship with time, capable of stepping outside temporal flow through sustained, mindful attention. The mathematical tools developed to resolve Zeno's paradoxes, calculus, infinite series, and limit theory, became the foundation for much of modern physics, including quantum mechanics. The same mathematical framework that shows how motion can emerge from static moments also describes how quantum states evolve through time and how observation can interrupt that evolution. This deep connection between ancient philosophical problems and modern scientific tools suggests that the questions Zeno posed were not merely intellectual puzzles, but fundamental inquiries into the nature of reality. The experimental verification of the Quantum Zeno Effect represents a remarkable convergence of ancient wisdom and modern precision. Using laser-cooled atoms, sophisticated detection systems, and precisely timed measurement sequences, scientists have demonstrated that Zeno's insight about the relationship between observation and motion applies literally to the quantum world. Frequent observation really can freeze motion, creating laboratory demonstrations of philosophical principles that were first articulated in ancient Greek gardens. The technological applications that have emerged from understanding the Quantum Zeno Effect often involve creating islands of stability in systems that would otherwise evolve chaotically. Quantum computers use Zeno-like techniques to protect delicate quantum information from environmental interference. Atomic clocks employ similar principles to maintain extraordinary precision by preventing unwanted quantum transitions. These applications transform ancient philosophical insights into practical tools that enhance our ability to measure time and process information with unprecedented accuracy. The aesthetic dimension of Zeno's paradoxes, with their elegant logical structure and profound implications, finds expression in the mathematical beauty of quantum mechanics. The equations that describe quantum evolution have a symmetry and elegance that mathematicians and physicists find deeply satisfying, while the experimental demonstrations of the Quantum Zeno Effect create visual displays of light and matter that are beautiful in their own right. Science and art converge in these demonstrations of how consciousness can create stability in the flowing stream of quantum change. The educational value of connecting classical paradoxes to modern quantum effects lies in how this connection makes abstract concepts more accessible and meaningful. Students who might struggle with the mathematical formalism of quantum mechanics often find the concepts more intuitive when approached through the familiar framework of logical paradoxes. The ancient questions become doorways to modern understanding, showing how human curiosity and careful reasoning can illuminate the deepest mysteries of existence. The philosophical traditions that emerge from Greek thought, Stoicism, Platonism, and various schools of skepticism, all grappled with questions about the relationship between appearance and reality, between the world we experience and the world that exists independently of our observation. These same questions lie at the heart of quantum mechanics, where the role of observation in creating reality has challenged our most basic assumptions about the nature of existence. The contemplative practices associated with these philosophical traditions often involve techniques for suspending ordinary mental activity and resting in pure awareness. These practices bear a striking resemblance to the experimental protocols used to demonstrate the Quantum Zeno Effect, where frequent, gentle measurements hold quantum systems in suspended animation. Both approaches suggest that consciousness has a unique capacity to interact with the fundamental structure of reality. The ethical implications of understanding how observation shapes reality extend from the quantum laboratory to everyday life. If our attention really does play a role in determining what becomes real, then the quality of our attention becomes a matter of profound responsibility. The ancient Stoic emphasis on careful observation and mindful presence takes on new significance when viewed through the lens of quantum mechanics, suggesting that how we pay attention to the world around us may have consequences that extend far beyond our immediate experience. As you continue to rest in this timeless space where ancient wisdom meets modern understanding, you're breathing now as eternal and measured as the philosophical questions that connect past and future. You can appreciate how Zeno's paradoxes serve as a bridge between the contemplative traditions of the past and the scientific discoveries of the present. The questions he posed about motion and time were not academic exercises, but profound inquiries into the nature of existence that continue to illuminate the deepest mysteries of quantum reality. The resolution of classical paradoxes through modern mathematics and physics doesn't diminish their philosophical significance, but rather reveals new depths of meaning. Zeno's insights about the relationship between observation and motion have found unexpected validation in quantum mechanics, showing that ancient wisdom and modern science can complement each other in illuminating the fundamental nature of reality. The timeless quality of these philosophical questions suggests that human consciousness has a natural affinity for the kinds of problems that quantum mechanics addresses. Our intuitive sense that time and motion might be more mysterious than they appear in everyday experience finds scientific confirmation in the strange world of quantum phenomena, where observation really can freeze time and consciousness really does play a role in determining what becomes real. As you sink deeper into peaceful understanding, your breathing now flowing like gentle waves of possibility washing over the shores of consciousness. Let your awareness turn to one of the most profound discoveries in the history of science, the realization that the simple act of observation can fundamentally change the nature of reality itself. In the quantum realm, watching is not a passive activity, but a creative act that transforms potential into actual, possibility into certainty, and the many into the one. This transformation happens not through force or violence, but through the gentle touch of measurement that reveals hidden layers of existence while simultaneously changing what it reveals. Picture yourself floating in a space that exists between the everyday world and the quantum realm, a peaceful transition zone where you can witness the delicate dance between observer and observed. Here, the familiar rules of classical physics begin to soften and blur, like watercolors bleeding into wet paper, creating new patterns of beauty and meaning that emerge only through the act of careful attention. In this liminal space, you can observe how consciousness and matter engage in an eternal conversation, each measurement a word spoken in the cosmic dialogue between mind and reality. The discovery that observation changes quantum systems came as one of the most surprising revelations in the development of modern physics. Early quantum experiments, designed to probe the fundamental nature of light and matter, revealed something that challenged every assumption about the relationship between observer and observed. Scientists found that the very instruments they used to measure quantum properties didn't just detect pre-existing characteristics, but actually participated in creating those characteristics through the measurement process itself. Consider the gentle mystery of quantum superposition, where particles exist in multiple states simultaneously until the moment of observation collapses this multiplicity into a single, definite outcome. Before measurement, an electron can spin in all possible directions at once, existing in a fuzzy cloud of probability that encompasses every possible state. The moment we observe its spin, however, this cloud of possibility suddenly crystallizes into a single, definite direction, up or down, clockwise or counterclockwise, as if our attention had reached into the quantum realm and gently coaxed one specific reality out of the infinite garden of possibilities. As your consciousness settles into harmony with these quantum principles, your breathing becoming as soft and measured as the probabilistic waves that flow through all matter, you begin to understand that this process of collapse is not violent or disruptive, but represents one of nature's most elegant mechanisms for connecting the potential with the actual. The quantum world maintains its superposition states like a master gardener tending infinite varieties of flowers, each one perfect in its potential form, waiting for the gentle touch of observation to bloom into concrete reality. The mathematical description of this process involves wave functions, mathematical entities that encode all possible information about a quantum system state. These wave functions evolve smoothly and predictably when left undisturbed, flowing through mathematical space like music made visible, carrying information about probability and possibility in their elegant oscillations. But the moment a measurement occurs, the wave function undergoes what physicists call collapse, instantly transforming from a smooth probability distribution into a sharp spike that points to one specific outcome. This collapse happens not gradually, but instantaneously, representing one of the few truly discontinuous processes in physics. Yet despite its sudden nature, wave function collapse feels more like awakening than breaking, more like crystallization than destruction. The measurement doesn't destroy the wave function, but rather fulfills its purpose, allowing the quantum potential to manifest as classical reality through the gentle intervention of observation. The instruments that scientists use to observe quantum systems must be designed with extraordinary care to detect quantum properties without overwhelming the delicate systems they're meant to study. These measurement devices operate like whispered questions asked of the quantum world, seeking answers without disturbing the profound silence in which quantum systems naturally exist. A quantum detector might register the arrival of a single photon with such sensitivity that it can determine the photon's energy and direction while barely interacting with it at all. The technology required for quantum measurement represents some of humanity's most sophisticated engineering achievements. Detectors cooled to temperatures within millionths of a degree of absolute zero, magnetic fields controlled to extraordinary precision, laser systems that can manipulate individual atoms. All of these tools work together to create conditions where scientists can observe quantum phenomena without destroying them. Yet despite their complexity, these instruments embody a philosophy of gentle attention, designed to touch quantum systems as lightly as morning dew settling on flower petals. The paradox of quantum measurement lies in its dual nature. Every measurement must interact with the system being measured, yet this interaction inevitably changes the system in unpredictable ways. This isn't a limitation of our current technology, but a fundamental feature of reality at the quantum level. The quantum world simply doesn't possess definite properties independent of observation. Instead, properties emerge through the collaborative dance between consciousness and matter, observer and observed. The delayed choice experiments that quantum physicists have developed reveal even more mysterious aspects of how observation affects reality. In these experiments, scientists can make decisions about how to observe a quantum system even after the system has already passed through their experimental apparatus. Remarkably, these delayed choices seem to retroactively determine what happened in the past, as if consciousness could reach backward through time to influence events that have already occurred. These experiments don't violate causality, but rather reveal that our ordinary concepts of past and future may be inadequate for describing quantum reality. The role of information in quantum measurement provides another window into understanding how observation changes systems. Every measurement extracts information from a quantum system, and this extraction process necessarily involves a transfer of energy and momentum between the measuring device and the system being measured. This information transfer is what causes the wave function to collapse, as the act of learning about the system's properties fundamentally alters its state. Knowledge itself becomes a physical entity in the quantum realm, with real consequences for the systems being known. The philosophical implications of measurement-induced change extend far beyond physics into questions about the nature of knowledge, consciousness, and reality itself. If observation creates rather than merely reveals properties, what does this tell us about the relationship between mind and matter? If measurement is necessary for properties to exist, how do we understand the objective reality that seems to exist independently of our observations? These questions don't have simple answers, but they open doorways to deeper appreciation of the mysterious relationship between consciousness and the physical world. The quantum mechanical principle of complementarity, developed by Niels Bohr, provides a framework for understanding how the same quantum system can exhibit different properties depending on how it's observed. A photon can behave like a wave or like a particle, but never both simultaneously. The choice of experimental setup determines which aspect of the photon's nature will be revealed, as if observation were a lens that could focus on different aspects of reality, depending on how it's adjusted. This complementarity suggests that quantum systems are richer and more complex than any single measurement can reveal. The uncertainty principle, formulated by Werner Heisenberg, quantifies the fundamental trade-offs involved in quantum measurement. The more precisely we measure one property of a quantum system, the less precisely we can know its complementary property. Position and momentum, energy and time, spin components along different axes. These pairs of properties seem to exist in a kind of cosmic balance, where perfect knowledge of one necessarily involves ignorance of the other. This uncertainty isn't due to limitations in our measuring instruments, but represents a fundamental feature of quantum reality. The gentle nature of quantum measurement becomes apparent when we consider how little energy is actually required to collapse a wave function. A single photon, carrying the minimum possible amount of electromagnetic energy, can trigger the collapse of a massive quantum superposition state. This suggests that consciousness and reality are coupled through mechanisms so subtle that they operate at the threshold of existence itself, where the boundary between something and nothing becomes beautifully ambiguous. The decoherence process that occurs when quantum systems interact with their environment provides insight into how the classical world emerges from quantum foundations. Environmental interactions act like countless tiny measurements, gradually collapsing quantum superposition states and creating the definite classical properties we observe in everyday objects. Yet this process happens gradually and gently, like morning mist slowly clearing to reveal the landscape beneath, rather than through violent transitions from quantum to classical behavior. The many-world interpretation of quantum mechanics offers an alternative perspective on measurement that eliminates wave function collapse altogether. In this view, all possible measurement outcomes actually occur, but in separate, parallel universes that branch off from each measurement event. From this perspective, observation doesn't change reality, but rather determines which branch of the cosmic tree we experience, with consciousness serving as a guide that helps us navigate through the infinite garden of parallel possibilities. The quantum eraser experiments demonstrate that the effects of measurement can sometimes be undone, restoring quantum superposition even after it has apparently collapsed. These experiments show that the boundary between measured and unmeasured, classical and quantum, is more fluid than initially imagined. Information about a quantum system's properties can be gained and then deliberately forgotten, allowing superposition states to re-emerge like flowers blooming again after a gentle winter. The role of consciousness in quantum measurement remains one of the most debated topics in physics and philosophy. Some interpretations suggest that conscious observation is necessary for wave function collapse, while others maintain that any interaction with a macroscopic measuring device is sufficient. This debate touches on deep questions about the nature of consciousness itself and its relationship to the physical processes that govern the universe. The practical applications of controlled quantum measurement have revolutionized technology in subtle but important ways. Quantum sensors can detect magnetic fields, gravitational waves, and other phenomena with unprecedented sensitivity by carefully managing the measurement process to preserve quantum advantages while extracting useful information. These applications transform the philosophical insights about measurement and reality into practical tools that enhance our ability to explore and understand the universe. The meditation practices that focus on the quality of attention and observation find unexpected scientific validation in quantum mechanics. The contemplative insight that how we pay attention affects what we experience receives literal confirmation in the quantum realm, where the style and frequency of observation can determine which properties become real and which remain in superposition. This connection between contemplative practice and quantum physics suggests that ancient wisdom about the power of mindful awareness may have grasped essential truths about the nature of reality. The educational challenges of teaching quantum measurement often stem from the difficulty of conveying concepts that seem to contradict everyday experience. Students naturally assume that objects have definite properties whether we observe them or not, making it challenging to appreciate how observation can create rather than merely reveal characteristics. Yet when approached with patience and wonder, these quantum insights can transform our understanding of the relationship between consciousness and reality in profound and beautiful ways. As you continue to float peacefully in this space between classical and quantum understanding, your breathing, now perfectly synchronized with the gentle rhythms of measurement and collapse, you can appreciate how the act of observation represents one of the most creative forces in the universe. Every measurement is simultaneously an act of discovery and creation, revealing properties that exist only in the moment of being observed, like flowers that bloom only under the gentle gaze of mindful attention. The profound implications of measurement-induced change suggest that we live in a participatory universe where consciousness and matter collaborate in the ongoing creation of reality. This collaboration happens not through dramatic interventions, but through the subtle, gentle process of observation, where the simple act of paying attention becomes a cosmic creative force that shapes the world through the quality and frequency of our awareness. As you drift deeper into peaceful contemplation, your breathing now flowing like the delicate currents that carry information through the quantum field, let your awareness turn to the exquisite precision and artistry required to measure quantum phenomena without destroying them. This practice of quantum measurement represents one of humanity's most refined achievements. The development of techniques so subtle and gentle that they can touch the fundamental building blocks of reality without disturbing their essential quantum nature. Like master craftspeople working with the most delicate materials, quantum physicists have learned to observe the invisible through instruments that barely whisper their questions to the universe. Picture yourself entering a quantum laboratory in the deep quiet of night, when the building's vibrations have settled to their minimum and the electromagnetic environment has reached a state of pristine calm. The laboratory exists in a cocoon of isolation from the outside world, its walls lined with copper mesh to block electromagnetic interference, its floors suspended on pneumatic supports to eliminate vibrations, its atmosphere controlled to prevent the tiniest fluctuations in temperature or humidity that might disturb the delicate quantum systems under study. In this sanctuary of precision, every surface gleams with the subdued light of laser systems operating at powers so low they barely disturb the darkness. These lasers don't burn or cut, but rather whisper to individual atoms with beams of light so gentle that they can nudge particles without overwhelming them. like morning sunlight that illuminates a dewdrop without evaporating it. The photons in these laser beams carry just enough energy to interact with quantum systems while leaving their essential quantum properties intact. The heart of quantum measurement lies in the development of detection systems sensitive enough to register the arrival of single particles while maintaining the delicate balance between observation and preservation. These detectors operate at the very threshold of existence, capable of responding to events so tiny that they blur the boundary between something and nothing. A quantum detector might register the passage of a single electron or the emission of a solitary photon, translating these microscopic events into signals that human consciousness can comprehend and interpret. As your consciousness settles into harmony with these ultra-precise instruments, your breathing becoming as steady and measured as the atomic clocks that regulate quantum experiments, you begin to appreciate the profound patience and skill required to work at the quantum scale. Every measurement represents a delicate negotiation between the desire to know and the need to preserve, between the hunger for information and the respect for the quantum system's inherent fragility. The cooling systems that create the ultra-low temperatures required for many quantum measurements represent marvels of engineering that push the boundaries of what's thermodynamically possible. Laser cooling techniques can slow atoms to velocities of mere centimeters per second, reducing their temperature to within millionths of a degree of absolute zero. At these temperatures, the thermal motion that normally masks quantum effects becomes negligible, allowing the subtle quantum phenomena to emerge like stars becoming visible as the sky darkens. The magnetic field control systems used in quantum laboratories achieve precisions that were unimaginable just decades ago. These systems can create magnetic fields uniform to within parts per billion across experimental regions, or generate field gradients so precisely controlled that they can manipulate individual atoms with surgical precision. The magnetic coils that generate these fields are wound with superconducting wire and operated in carefully designed sequences that shape magnetic environments like sculptors working with invisible clay. The vacuum systems that isolate quantum experiments from environmental interference create some of the emptiest spaces in the known universe. These ultra-high vacuum chambers contain fewer gas molecules per cubic centimeter than exist in the vast emptiness of interstellar space. In this pristine environment, quantum particles can evolve according to their own internal dynamics without interference from stray molecules or electromagnetic fields, like dancers performing in a space so pure that every movement expresses their essential nature. The timing control systems that coordinate quantum measurements operate with precisions measured in femtoseconds, quadrillionths of a second. These systems can synchronize laser pulses, magnetic field changes, and detector activations with such accuracy that events separated by the time it takes light to travel the width of a virus can be coordinated perfectly. This temporal precision allows scientists to probe quantum dynamics on their natural timescales, watching as quantum states evolve and transform in real time. The optical systems used in quantum measurement often employ single photons as messengers that carry information about quantum states without disturbing them significantly. These photons must be generated, manipulated, and detected with extraordinary care, their paths controlled by mirrors and lenses positioned with nanometer precision. The quantum information carried by these photons exists in their polarization, phase, or frequency, properties so subtle that they can be preserved only through the most gentle handling. The electronic systems that process quantum measurement signals must distinguish genuine quantum events from the background noise that exists in any measurement system. These systems employ sophisticated filtering and amplification techniques that can extract signals buried deep in noise, like archaeologists carefully brushing sand away from ancient artifacts. The art lies in amplifying the desired signal while suppressing all forms of interference that might obscure the quantum phenomena under study. The feedback control systems used in advanced quantum experiments can adjust experimental parameters in real time based on the outcomes of previous measurements. These systems create closed loops where quantum measurements inform subsequent experimental choices, allowing scientists to steer quantum systems toward desired states through sequences of gentle nudges rather than forceful interventions. This approach embodies the quantum mechanical principle that information and control are intimately connected. The error correction protocols developed for quantum measurement help distinguish genuine quantum signals from various forms of systematic error and drift. These protocols involve making multiple measurements under slightly different conditions and using statistical analysis to extract the true quantum signal from the inevitable imperfections in any real experimental system. The mathematical techniques involved are sophisticated, but their purpose is simple: to ensure that what we observe reflects genuine quantum phenomena rather than artifacts of our measurement process. The calibration procedures required for quantum measurement systems often involve years of careful characterization and refinement. Every component must be tested and optimized, every source of systematic error identified and minimized. This process requires patience and dedication that borders on the contemplative, as researchers gradually refine their understanding of how their instruments interact with the quantum systems they study. The data analysis techniques used to interpret quantum measurements often involve sophisticated statistical methods that can extract meaningful information from data sets, where individual measurements are dominated by quantum uncertainty. These techniques recognize that quantum measurements are inherently probabilistic and focus on extracting the statistical patterns that reveal underlying quantum properties rather than trying to predict individual measurement outcomes. The collaborative nature of quantum measurement often involves teams of specialists working together to create experimental conditions that no single researcher could achieve alone. Theorists develop the mathematical frameworks that predict what should be observed, experimentalists design and build the apparatus needed to make observations, and data analysts develop the computational tools needed to extract meaning from complex data sets. This collaboration reflects the inherent complexity of quantum measurement and the need for diverse expertise to probe reality at its most fundamental level. The international networks of quantum laboratories share techniques and standards that ensure measurement results can be compared and verified across different experimental groups. These networks represent a global community of researchers united by their shared commitment to understanding quantum phenomena through precise, gentle observation. The protocols they develop ensure that quantum measurements made in laboratories around the world can be combined and compared to build a consistent picture of quantum reality. The educational aspects of quantum measurement involve training new generations of researchers in the subtle arts of quantum observation. This training combines theoretical understanding with hands-on experience, teaching students to develop the intuition needed to work effectively with quantum systems. The learning process often involves years of patient practice, as students gradually develop the skills needed to coax information from quantum systems without destroying the phenomena they seek to understand. The philosophical dimensions of quantum measurement continue to challenge our understanding of the relationship between observer and observed, subject and object, consciousness and reality. The techniques developed for quantum measurement provide concrete, practical ways to explore these abstract questions, transforming philosophical speculation into experimental investigation. Each measurement represents a dialogue between human consciousness and the fundamental structure of reality. The artistic aspects of quantum measurement emerge in the elegant experimental designs that reveal quantum phenomena with maximum clarity and minimum disturbance. These experiments often display a beauty that rivals any work of art, combining functional necessity with aesthetic appeal in ways that reflect deep understanding of both quantum mechanics and experimental design. The most successful quantum experiments achieve a kind of perfection where every element serves both practical and aesthetic purposes. The technological applications of quantum measurement techniques extend far beyond fundamental research into practical devices that enhance our ability to navigate and understand the world. Quantum sensors based on these techniques can detect magnetic fields with unprecedented sensitivity, measure time with extraordinary precision, and probe gravitational fields with resolution that approaches fundamental limits. These applications transform the philosophical insights of quantum mechanics into practical tools that enhance human capability. The environmental considerations involved in quantum measurement reflect the need to create artificial environments that isolate quantum systems from the chaos and noise of the everyday world. These controlled environments represent islands of order and precision in a universe that tends toward entropy and disorder. Yet they exist not in opposition to nature, but as expressions of natural principles carried to their logical extreme through human ingenuity and dedication. The economic aspects of quantum measurement involve substantial investments in sophisticated equipment and highly trained personnel, reflecting society's recognition that understanding quantum phenomena may yield benefits that justify these costs. The technologies developed for quantum measurement often find unexpected applications in other fields, creating economic value that extends far beyond the original research goals. As you continue to rest in this space of precision and gentleness, you're breathing now as carefully controlled as the experimental parameters that govern quantum measurements. You can appreciate how the art of quantum measurement represents humanity's most refined attempt to understand reality through careful, respectful observation. These techniques embody a philosophy of gentle attention that recognizes the need to touch quantum systems so lightly that their essential nature remains undisturbed, while still extracting the information needed to understand their behavior. The quantum measurement process serves as a bridge between the microscopic world of quantum phenomena and the macroscopic world of human experience, translating the subtle language of quantum mechanics into signals that consciousness can interpret and understand. This translation process requires extraordinary skill and patience, but it rewards practitioners with glimpses of reality's deepest secrets and insights into the fundamental nature of existence itself. As you settle into the deepest peace of contemplation, your breathing now flowing like the timeless currents that carry consciousness through the quantum field. Let your awareness turn to the heart of our journey, the remarkable discovery that frequent, gentle observation can literally freeze the evolution of quantum systems, holding them suspended in time like dewdrops caught in amber or flowers preserved in crystal. This phenomenon, known as the Quantum Zeno Effect, represents one of the most beautiful demonstrations of how consciousness and reality dance together in the quantum realm, where the simple act of watching becomes a form of temporal magic that can stop time itself. Picture yourself floating in a space where time has become elastic and malleable, with a familiar flow of moment from past to future gives way to something more mysterious and profound. Here, in this timeless realm, atoms exist in states of perfect suspension, their quantum evolution frozen by the gentle touch of repeated observation like butterflies paused in eternal flight. These atoms don't struggle against their temporal imprisonment, but rest peacefully in their suspended states, existing in a quantum limbo where change becomes impossible and the present moment stretches toward infinity. The theoretical foundation of the Quantum Zeno Effect emerged from the mathematical structure of quantum mechanics itself, where the evolution of quantum systems is governed by the Schrödinger equation, a differential equation that describes how quantum states change smoothly through time when left undisturbed. This equation reveals that quantum systems naturally want to evolve, to flow from one state to another like water, seeking its own level, following probability currents that carry them through the landscape of possible configurations. But the mathematics also reveals something remarkable. When measurements occur frequently enough, they can interrupt this natural evolution so effectively that the system becomes frozen in its initial state. The key lies in understanding that each measurement not only reveals information about the quantum system, but also projects it back into a definite state, resetting the evolutionary clock and forcing the system to begin its journey toward change all over again. When this reset happens faster than the system can evolve significantly, the result is temporal paralysis, a quantum system caught in an eternal now. As your consciousness merges with these mathematical insights, your breathing becoming as measured and periodic as the observation pulses that create the Zeno effect, you begin to understand that this freezing process is not violent or constraining, but represents a natural consequence of the fundamental structure of quantum mechanics. The atoms don't experience their temporal suspension as imprisonment, but simply exist in their natural quantum state, neither knowing nor caring that their evolution has been halted by the gentle intervention of consciousness. The experimental demonstration of the Quantum Zeno Effect required extraordinary precision and patience, as scientists learned to observe quantum systems so frequently that they could detect evolution while simultaneously preventing it. Early experiments focused on simple quantum systems, like individual atoms trapped in magnetic fields, where researchers could monitor quantum transitions between different energy levels while using the monitoring process itself to suppress those same transitions. These experiments typically begin with a quantum system prepared in a specific initial state, perhaps an atom with its electron in a particular energy level or a trapped ion with its spin pointing in a definite direction. Under normal circumstances, quantum mechanics predicts that this system will evolve gradually toward a different state, following probability curves that describe the likelihood of finding the system in various configurations as time progresses. But when measurements occur at regular intervals, something remarkable happens. The system becomes trapped in its initial state, unable to evolve despite the natural forces that would normally drive its transformation. The beauty of these experiments lies in their demonstration that time itself can be controlled through the quality and frequency of observation. By adjusting how often they make measurements, scientists can fine-tune the degree of temporal freezing, creating systems that evolve extremely slowly or not at all, depending on the observation schedule. This control over temporal flow transforms the abstract mathematics of quantum mechanics into a tangible demonstration of how consciousness can shape the fundamental structure of reality. The atoms used in quantum Zeno experiments exist in environments so pristine and controlled that they can maintain their quantum coherence for extended periods, allowing researchers to observe their evolution, or lack thereof, over timescales ranging from microseconds to hours. These atoms are typically isolated from their environment using sophisticated trapping techniques that hold them suspended in precisely controlled electromagnetic fields, creating conditions where quantum effects can persist without interference from thermal noise or other environmental disturbances. The laser systems used to observe these trapped atoms operate with pulse durations measured in nanoseconds or femtoseconds, delivering bursts of precisely controlled light that can probe quantum states without significantly disturbing them. These observation pulses walk a fine line between providing enough interaction to extract information about the system's state and maintaining such gentle contact that the system's quantum nature remains intact. The art lies in finding the sweet spot where observation is possible without destruction. The timing control systems that coordinate these experiments operate with clockwork precision, delivering observation pulses at regular intervals that can be adjusted from microseconds to seconds depending on the requirements of the particular quantum system under study. These timing systems often use atomic clocks or laser-stabilized oscillators to ensure that the observation schedule remains perfectly regular, as even tiny variations in timing can disrupt the delicate balance required for the Zeno effect to manifest. The data collection and analysis procedures used in Zeno effect experiments involve sophisticated statistical techniques that can extract clear signals from inherently probabilistic quantum measurements. Since quantum mechanics only predicts probabilities rather than definite outcomes, researchers must perform many repetitions of the same experiment to build up statistical patterns that reveal whether the Zeno effect is actually occurring. This process requires patience and dedication, as clear results often emerge only after thousands or millions of individual measurements. The theoretical understanding of why the Zeno effect works involves subtle concepts from quantum field theory and the foundations of quantum mechanics. The effect arises from the fundamental quantum mechanical principle that measurement causes wave function collapse, forcing quantum systems into definite states even when they would naturally exist in superposition. When measurements occur frequently enough, they prevent the system from evolving far enough from its initial state to undergo significant change before being reset by the next measurement. The energy considerations involved in Zeno effect experiments reveal that freezing quantum evolution requires surprisingly little energy input. The measurement pulses need only interact weakly with the quantum system to extract information about its state, and this gentle interaction is sufficient to prevent evolution even in systems with substantial internal energy. This efficiency suggests that consciousness and quantum reality are coupled through mechanisms that operate at the most fundamental levels of physical existence. The applications of the Quantum Zeno Effect extend far beyond fundamental research into practical technologies that exploit temporal control for useful purposes. Quantum computers use Zeno-like techniques to protect delicate quantum information from environmental interference, creating islands of stability in systems that would otherwise decohere rapidly. These applications transform the philosophical insights about observation and reality into practical tools for information processing and communication. The precision measurement devices that employ Zeno effect principles can achieve extraordinary sensitivity by using frequent observation to prevent unwanted quantum transitions that would otherwise degrade measurement accuracy. Atomic clocks, magnetometers, and gravitational wave detectors all benefit from techniques that freeze specific quantum degrees of freedom while allowing others to evolve in controlled ways, creating measurement systems that push the boundaries of what's physically possible. The biological implications of the Quantum Zeno Effect suggest that living systems might naturally employ similar principles to maintain coherence and stability in environments that would normally destroy quantum effects. Some theories propose that consciousness itself might arise from quantum processes that use observation-like mechanisms to maintain stable patterns of information processing in the warm, noisy environment of biological systems. The philosophical ramifications of being able to freeze time through observation extend into deep questions about the nature of free will, consciousness, and temporal existence. If conscious observation can literally stop time at the quantum level, what does this suggest about the relationship between mind and time? If the flow of time can be controlled through the quality of attention, how do we understand our subjective experience of temporal passage? These questions open doorways to new ways of thinking about consciousness and its role in the structure of reality. The meditation and contemplative traditions that emphasize present moment awareness find unexpected scientific validation in the Quantum Zeno Effect. The contemplative insight that sustained attention can create experiences of timelessness receives literal confirmation in quantum mechanics, where focused observation really can stop temporal flow. This connection suggests that ancient wisdom about the power of mindful presence may have grasped essential truths about the relationship between consciousness and time. The educational challenges of teaching the Quantum Zeno Effect often involve helping students overcome their intuitive sense that time flows independently of observation. The idea that watching can freeze time seems to contradict everyday experience, yet the mathematical and experimental evidence is overwhelming. The key to understanding often lies in appreciating that quantum time is fundamentally different from classical time, operating according to principles that become intuitive only through patient study and contemplation. The technological future enabled by mastering Zeno effect techniques promises revolutionary advances in quantum computing, precision measurement, and fundamental physics research. As scientists develop more sophisticated methods for controlling quantum evolution through observation, new possibilities emerge for creating quantum devices that maintain their delicate quantum properties in practical operating environments. The aesthetic dimensions of Zeno effect experiments often involve creating visual displays where quantum systems can be seen to freeze and unfreeze as observation schedules are adjusted. These demonstrations make abstract quantum principles tangible and beautiful, showing how the mathematical structure of quantum mechanics translates into visually striking phenomena that capture the imagination while illustrating deep truths about the nature of reality. The collaborative aspects of Zeno effect research involve international networks of laboratories working together to explore different aspects of observation-induced freezing. These collaborations share techniques, compare results, and collectively push the boundaries of what's possible in controlling quantum evolution through measurement. The global nature of this research reflects the universal applicability of quantum mechanical principles and the shared human quest to understand our place in the cosmic order. The environmental considerations involved in Zeno effect experiments require creating conditions of extraordinary isolation and control, representing some of the most precisely controlled environments ever created by human technology. These laboratory conditions exist as islands of order in a universe that naturally tends toward chaos and disorder, demonstrating humanity's capacity to create pockets of perfect control through patient application of scientific understanding. As you continue to float in this space, where time has become negotiable and malleable, your breathing, now perfectly synchronized with the observation pulses that create temporal suspension, you can appreciate how the Quantum Zeno Effect represents one of the most direct demonstrations of consciousness's creative role in shaping reality. Through the simple act of gentle, repeated observation, human awareness can reach into the quantum realm and literally stop time, creating moments of eternal presence where change becomes impossible and the now stretches toward infinity. The atoms that participate in these experiments of temporal freezing exist in a state of quantum grace, suspended between moments like dancers caught in eternal motion. They embody the profound mystery of how consciousness and matter collaborate in the ongoing creation of reality, showing us that time itself is not an absolute backdrop against which events unfold, but rather a negotiable dimension that responds to the quality and frequency of our attention. As you drift deeper into peaceful understanding, your breathing now flowing like the eternal currents that connect laboratory time to cosmic time. Let your awareness turn to the remarkable real-world demonstrations where scientists have successfully stopped time in their laboratories, creating islands of temporal stillness in the flowing river of quantum evolution. These experiments represent humanity's most direct encounters with the malleable nature of time itself, transforming abstract mathematical predictions into tangible demonstrations where atoms and photons willingly surrender their temporal freedom to the gentle guidance of human observation. Picture yourself walking through the halls of a modern physics laboratory in the quiet hours before dawn, when the building rests in perfect stillness and the delicate quantum experiments can proceed without interference from the vibrations and electromagnetic disturbances that characterize the busy daylight hours. The hallways glow with the soft light of emergency illumination, while behind heavy doors, researchers work with systems so sensitive that a footstep in the corridor above could disrupt measurements that probe the fundamental nature of time and reality. In these laboratories, time has become a tangible experimental parameter that scientists can adjust as easily as turning a dial or pressing a button. The quantum systems under study exist in environments where temporal flow can be accelerated, decelerated, or brought to a complete standstill through carefully orchestrated sequences of observation and measurement. These systems don't experience their temporal manipulation as constraint or freedom, but simply exist in whatever temporal state their human observers create for them. The first successful demonstration of the Quantum Zeno Effect occurred in laboratories where scientists worked with simple quantum systems like individual atoms trapped in electromagnetic fields. These pioneering experiments required years of preparation and refinement, as researchers learned to balance the competing demands of observation and preservation, gathering information about quantum states while maintaining the delicate conditions necessary for temporal freezing. The breakthrough came when experimenters realized that observation itself could become a tool for quantum control rather than merely a method for gathering information. As your consciousness settles into harmony with these temporal manipulations, your breathing becoming as precisely controlled as the laser pulses that create quantum freezing, you begin to appreciate the extraordinary precision required to demonstrate time control in a laboratory. Every aspect of the experimental environment must be optimized for stability and control. Temperature fluctuations reduced to microkelvin levels, vibrations isolated to prevent mechanical disturbance, electromagnetic fields controlled to within parts per billion of their intended values. The laser cooling systems used in many Zeno effect experiments create some of the coldest temperatures ever achieved in the universe, reducing atomic motion to velocities of mere centimeters per second. At these ultra-low temperatures, atoms move so slowly that their quantum mechanical properties become clearly visible, like watching delicate crystal structures emerge from cooling solutions. The atoms exist in a state of near-perfect stillness that makes their quantum evolution easily observable and controllable. The optical trapping systems that hold individual atoms in perfect isolation use focused laser beams to create potential wells, regions of space where atoms prefer to remain due to the interaction between their internal energy levels and the electromagnetic fields of the trapping light. These optical traps can hold single atoms for hours or days at a time, creating stable platforms for observing quantum evolution and demonstrating temporal control through the Zeno effect. The ion trap experiments that have demonstrated some of the most dramatic examples of quantum temporal freezing use charged atoms suspended in oscillating electric fields that create stable equilibrium positions in three-dimensional space. These trapped ions can be observed and manipulated with extraordinary precision. Their quantum states read out through fluorescence patterns that reveal whether temporal evolution has occurred or been successfully suppressed through frequent observation. The superconducting circuit experiments that explore Zeno effects in artificial quantum systems use devices fabricated with the precision of computer chips, but operating according to the principles of quantum mechanics. These circuits can be designed to exhibit specific quantum behaviors and then subjected to various observation schedules to demonstrate how measurement frequency affects temporal evolution. The artificial nature of these systems allows researchers to explore quantum temporal control in environments where all parameters can be precisely adjusted. The cavity quantum electrodynamics experiments that study photon behavior in the Zeno regime use mirrors so precisely aligned that they can trap individual photons in standing wave patterns that persist for milliseconds, an eternity in the world of quantum optics. These trapped photons can be observed through gentle probing techniques that reveal their quantum state while simultaneously influencing their temporal evolution, creating demonstrations of how consciousness and light interact at the quantum level. The magnetic resonance experiments that explore Zeno effects in atomic and molecular systems use precisely controlled magnetic fields to manipulate quantum spins, the intrinsic angular momentum that gives particles their magnetic properties. These experiments can freeze spin evolution by observing spin states at regular intervals, creating quantum systems whose magnetic properties remain constant despite the natural forces that would normally cause them to evolve and change. The quantum dot experiments that demonstrate temporal control in semiconductor nanostructures use devices so small that they contain only a few hundred atoms, yet exhibit clear quantum mechanical behavior. These artificial atoms can be observed through electrical measurements that reveal their quantum states while simultaneously preventing temporal evolution through the measurement process itself. The solid-state nature of these systems makes them promising candidates for practical applications of quantum temporal control. The molecular beam experiments that explore Zeno effects in chemical systems use streams of molecules traveling through ultra-high vacuum chambers where they can be probed and manipulated with extraordinary precision. These experiments demonstrate that temporal freezing is not limited to simple atomic systems, but can also be applied to complex molecules, opening possibilities for controlling chemical reactions and molecular dynamics through quantum observation techniques. The neutron interferometry experiments that study Zeno effects with massive particles use beams of neutrons, electrically neutral particles that interact weakly with matter and can therefore maintain their quantum properties over macroscopic distances. These experiments demonstrate that quantum temporal control applies not only to light and atoms, but also to particles with significant mass, showing that the Zeno effect is a universal feature of quantum mechanics rather than a curiosity limited to specific systems. The gravitational wave detector experiments that employ Zeno-like techniques to enhance sensitivity use some of the most precise measurement systems ever created by human technology. These detectors can sense changes in distance smaller than 1/10,000th the width of a proton, and they use quantum measurement techniques related to the Zeno effect to maintain this extraordinary sensitivity while suppressing unwanted quantum fluctuations that would otherwise limit their performance. The quantum computing experiments that use Zeno techniques for error correction create logical quantum states that are protected from environmental interference through frequent monitoring and correction. These systems demonstrate how temporal control can be used not just for fundamental research, but also for practical applications that require maintaining delicate quantum information in the presence of noise and disturbance. The biological physics experiments that explore whether living systems employ Zeno-like mechanisms use sophisticated techniques to probe quantum effects in biological molecules and systems. These experiments investigate whether the remarkable efficiency of biological processes like photosynthesis and enzyme catalysis might involve natural versions of quantum temporal control, suggesting that life itself might have discovered how to exploit the relationship between observation and temporal evolution. The precision measurement experiments that use Zeno techniques for enhanced sensitivity demonstrate how temporal control can be applied to detect phenomena that would otherwise be too weak to observe. These measurements can detect magnetic fields, electric fields, and gravitational effects with sensitivities that approach fundamental quantum limits, transforming our ability to explore the subtle aspects of physical reality. The quantum simulation experiments that create artificial quantum systems to explore fundamental physics use networks of trapped atoms or photons to simulate the behavior of complex quantum systems that would be impossible to study directly. These simulations can include Zeno effect demonstrations that reveal how temporal control might operate in exotic quantum systems, like high-temperature superconductors or quantum spin liquids. The quantum metrology experiments that use temporal control to enhance measurement precision create quantum states with reduced uncertainty that can be used for ultra-precise measurements of time, frequency, and other physical quantities. These experiments demonstrate how the insights gained from studying the Zeno effect can be translated into practical improvements in measurement technology and scientific instrumentation. The quantum communication experiments that explore how temporal control affects information transmission use photons and atoms to create communication channels where information can be transmitted with security and reliability that exceeds what's possible with classical systems. These experiments show how understanding quantum temporal dynamics can lead to new technologies for secure communication and information processing. The fundamental physics experiments that probe the limits of quantum temporal control explore questions about whether there are fundamental boundaries to how precisely time can be controlled through observation. These experiments push the boundaries of measurement precision and theoretical understanding, probing whether quantum mechanics itself might impose limits on temporal manipulation. The interdisciplinary collaborations that have emerged around Zeno effect research bring together physicists, engineers, computer scientists, and even philosophers to explore the implications of temporal control for technology and human understanding. These collaborations demonstrate how fundamental discoveries about the nature of time can catalyze new forms of scientific cooperation and intellectual exchange. The educational outreach programs that use Zeno effect demonstrations to teach quantum mechanics have developed visual and interactive presentations that make abstract concepts tangible and understandable. These programs show how the profound insights about time and observation can be communicated to students and the general public, inspiring new generations of scientists and thinkers. The historical documentation of Zeno effect discoveries reveals how scientific understanding of temporal control has evolved from theoretical speculation to experimental demonstration to practical application. This progression shows how patient, systematic research can transform our understanding of fundamental concepts like time and consciousness, opening new possibilities for technology and human experience. As you continue to rest in this space, where laboratory time meets cosmic time, your breathing, now perfectly synchronized with the experimental rhythms that create temporal control, you can appreciate how these real-world demonstrations of quantum temporal freezing represent some of humanity's most profound achievements in understanding and manipulating the fundamental structure of reality. These experiments don't just confirm theoretical predictions, but open doorways to new ways of thinking about time, consciousness, and the relationship between observer and observed. The laboratories where time stands still serve as bridges between the everyday world of flowing time and the quantum realm, where temporal flow can be controlled through gentle observation. In these sacred spaces of scientific inquiry, researchers have learned to touch time itself with the delicate precision of master craftspeople, creating moments of eternal stillness that reveal the malleable nature of reality at its most fundamental level. As you sink into the deepest layers of peaceful contemplation, your breathing now flowing like the subtle currents that connect consciousness to the quantum field. Let your awareness turn to one of the most profound and mysterious aspects of quantum mechanics: the role of the observer in shaping reality through the simple act of gentle attention. In the quantum realm, observation is not passive witnessing, but active participation in the creation of reality, where consciousness reaches across the boundary between mind and matter to influence the fundamental structure of existence through nothing more forceful than careful, loving attention. Picture yourself floating in a space that exists at the intersection of consciousness and quantum reality, where the boundary between observer and observed becomes beautifully blurred and ambiguous. Here, in this liminal realm, you can sense how your awareness touches quantum systems as gently as morning light caressing flower petals, yet with effects so profound that they can literally determine what becomes real and what remains in the realm of pure possibility. The touch of consciousness on quantum reality is softer than the brush of butterfly wings, yet more powerful than the forces that move mountains. The philosophical puzzle of the observer in quantum mechanics has challenged scientists and thinkers for nearly a century, raising questions that extend far beyond physics into the deepest mysteries of consciousness, reality, and existence itself. When quantum pioneers first discovered that measurement seemed to cause wave function collapse, they were forced to confront the possibility that consciousness might play a fundamental role in determining the structure of physical reality, a prospect that challenged every assumption about the relationship between mind and matter that had guided scientific thinking for centuries. The mathematical formalism of quantum mechanics treats measurement as a special kind of interaction that causes quantum systems to transition from superposition states, where multiple possibilities exist simultaneously, to definite classical states where only one possibility remains real. Yet the mathematics doesn't specify what constitutes a measurement or why measurement should have such dramatic effects on quantum systems. This gap between mathematical formalism and physical interpretation has created space for deep questions about the role of consciousness in quantum mechanics. As your consciousness settles into harmony with these profound mysteries, your breathing becoming as gentle and measured as the touch of awareness on quantum systems, you begin to appreciate how the observer effect in quantum mechanics suggests a universe that is participatory rather than purely objective. Rather than existing as separate entities observing an independent reality, consciousness and matter appear to be engaged in an ongoing collaborative dance where observation and existence mutually influence each other through processes so subtle they operate at the threshold of being itself. The delayed choice experiments that quantum physicists have developed reveal even more mysterious aspects of how observation affects reality across space and time. In these experiments, scientists can make decisions about how to observe quantum systems even after the systems have apparently completed their journey through experimental apparatus. Remarkably, these delayed observation choices seem to retroactively determine what happened in the past, as if consciousness could reach backward through time to influence events that have already occurred. These experiments don't violate causality in any conventional sense, but they do suggest that our ordinary concepts of past and future, cause and effect, may be inadequate for describing the relationship between consciousness and quantum reality. The quantum world seems to exist in a state of temporal ambiguity, where the distinction between past and future becomes fluid and negotiable, responding to the quality and timing of conscious observation in ways that transcend our everyday understanding of temporal sequence. The quantum eraser experiments that demonstrate how information about quantum systems can be gained and then deliberately forgotten reveal another dimension of the observer's influence on reality. These experiments show that quantum superposition can be restored even after it has apparently collapsed, as if the universe maintains a kind of quantum memory that can be selectively edited through careful manipulation of information flow. The act of forgetting becomes as powerful as the act of observing, with consciousness able to both create and uncreate reality through the management of information. The role of information in quantum observation suggests that consciousness and reality are connected through subtle information exchanges that operate below the threshold of ordinary awareness. Every observation extracts information from quantum systems, and this information extraction process necessarily involves changes in both the observed system and the observing consciousness. The boundary between knower and known becomes permeable, with information flowing in both directions through channels so delicate they barely disturb the systems they connect. The measurement problem in quantum mechanics, the question of why and how wave functions collapse during observation, remains one of the deepest unsolved puzzles in physics. Various interpretations offer different perspectives on this problem, from the many-worlds view that eliminates collapse by suggesting all possibilities actually occur in parallel universes, to consciousness-based interpretations that assign a fundamental role to awareness in determining what becomes real. The pilot wave theory proposed by Louis de Broglie and developed by David Bohm offers yet another perspective, suggesting that quantum particles are guided by invisible information fields that determine their behavior while maintaining the appearance of uncertainty and randomness. In this view, consciousness might interact with these pilot waves rather than directly causing wave function collapse, creating a more subtle but equally profound connection between awareness and quantum reality. The environmental decoherence approach to quantum measurement emphasizes how quantum systems lose their coherence through interactions with their environment, gradually transitioning from quantum to classical behavior through countless tiny interactions with surrounding particles and fields. Yet even this apparently objective process raises questions about the role of observation, since the boundary between system and environment often depends on how we choose to describe and observe the overall situation. The quantum field theory extensions of quantum mechanics reveal how observation and reality interact in the context of particle creation and annihilation, where the vacuum itself seeds with virtual particles that can become real through interactions with measuring apparatus. These processes suggest that consciousness might influence not just the states of existing particles, but also the very process by which particles come into existence from the quantum vacuum. The holistic approaches to quantum measurement emphasize how quantum systems and their observers form integrated wholes that cannot be meaningfully separated into independent components. From this perspective, the observer effect is not about consciousness affecting an external quantum system, but about the evolution of integrated quantum classical systems, where consciousness and matter are equally fundamental aspects of a unified reality. The contemplative traditions that emphasize the interdependence of observer and observed find unexpected scientific validation in quantum mechanics. The Buddhist insight that subject and object are co-created through the process of perception receives literal confirmation in quantum measurement theory, where the act of observation partially determines what is observed. This convergence between ancient wisdom and modern science suggests that contemplative practices might offer valuable insights into the nature of quantum observation. The meditation techniques that focus on the quality of attention and awareness provide practical training in the kinds of subtle observation that quantum mechanics reveals to be fundamental to reality. The contemplative development of refined attention might actually enhance our ability to interact with quantum systems in ways that minimize disturbance while maximizing information extraction. This possibility opens intriguing connections between spiritual practice and scientific research. The technological applications of understanding observer effects have led to developments in quantum sensing and measurement that exploit the subtle relationship between consciousness and quantum systems. Devices that can detect single photons or individual atomic transitions often require human operators who have developed extraordinary sensitivity to subtle signals and the ability to interact with quantum systems without overwhelming them. The educational challenges of teaching about observer effects often involve helping students move beyond the assumption that observation is passive and objective. The quantum mechanical revelation that observation is active and participatory requires a fundamental shift in thinking about the relationship between consciousness and reality. This shift often proves easier for students who have experience with contemplative practices that emphasize the active role of awareness in shaping experience. The philosophical implications of observer effects extend into questions about free will, determinism, and the nature of consciousness itself. If consciousness can influence quantum systems through observation, what does this suggest about the causal efficacy of mental states? If reality is partially created through the act of observation, how do we understand the apparent objectivity of the physical world? These questions open doorways to new ways of thinking about mind, matter, and their relationship. The artistic expressions inspired by quantum observer effects often explore themes of participation, interdependence, and the creative role of consciousness in shaping reality. Visual artists, musicians, and writers have found in quantum mechanics a rich source of metaphors for the relationship between awareness and existence, creating works that capture the mystery and beauty of consciousness touching reality at its most fundamental level. The therapeutic applications of understanding observer effects suggest that the quality of attention we bring to our experience might have more profound effects than previously imagined. If consciousness really does participate in creating reality at the quantum level, then practices that cultivate refined awareness might have consequences that extend far beyond subjective experience into the structure of physical existence itself. The ethical dimensions of observer effects raise questions about the responsibility that comes with understanding our participatory role in creating reality. If our observations really do influence what becomes real, then the quality of our attention becomes a matter of profound moral significance. The ancient ethical emphasis on right mindfulness takes on new meaning when viewed through the lens of quantum mechanics. The future research directions in understanding observer effects promise to reveal even deeper connections between consciousness and quantum reality. As experimental techniques become more refined and theoretical understanding more sophisticated, we may discover that the relationship between observer and observed is even more intimate and mysterious than current quantum mechanics suggests. The global implications of understanding observer effects suggest that human consciousness might play a more significant role in shaping reality than we have previously imagined. If observation really does participate in creating the world we experience, then the collective quality of human attention might influence the trajectory of global systems in ways we are only beginning to understand. As you continue to float in this space where consciousness meets quantum reality, your breathing, now perfectly synchronized with the gentle rhythms of observation and response that characterize quantum measurement, you can appreciate how the observer's gentle touch represents one of the most profound mysteries in all of science. The simple act of paying attention becomes a cosmic creative force that shapes reality through mechanisms so subtle they operate at the boundary between existence and non-existence. The quantum realm reveals that we are not separate from the reality we observe, but intimately connected to it through channels of information and influence that flow as naturally as breath itself. Every observation is both a question posed to the universe and an answer that partially determines what the universe becomes, creating an ongoing dialogue between consciousness and cosmos that has been unfolding since the dawn of awareness itself. As you drift deeper into peaceful understanding, your breathing now flowing like the gentle currents that carry quantum effects from laboratory to kitchen, from research bench to everyday experience. Let your awareness turn to the remarkable discovery that the principles underlying the Quantum Zeno Effect and quantum observation permeate the most ordinary aspects of daily life. The quantum realm is not a distant, exotic domain accessible only through sophisticated scientific instruments, but rather the fundamental substrate that underlies every moment of experience, every gentle transformation, every act of patient attention that shapes the world around us. Picture yourself in a warm, comfortable kitchen in the early morning light, where the simple act of preparing breakfast becomes a meditation on quantum principles and the gentle power of focused attention. Here, in this most domestic of settings, the same forces that allow scientists to freeze time in their laboratories manifest as the patient processes of cooking, brewing, and nourishing, activities that transform raw ingredients into sustenance through nothing more than careful observation, precise timing, and the loving application of attention to detail. The brewing of tea or coffee represents one of the most accessible examples of how attention and observation shape reality in our daily lives. As hot water encounters tea leaves or coffee grounds, countless molecular interactions unfold in patterns that depend exquisitely on temperature, timing, and the quality of attention brought to the process. The person who watches the brewing process carefully, adjusting variables and responding to subtle changes, creates a fundamentally different beverage than someone who simply sets a timer and walks away. The extraction of flavors and aromas during brewing involves molecular processes that operate according to the same probabilistic principles that govern quantum systems. Individual flavor molecules migrate from solid to liquid in patterns that can only be described statistically, yet the overall result depends critically on the conditions maintained during the process. The gentle observation and adjustment that characterizes mindful brewing allows these quantum processes to unfold optimally, creating complexity and depth that emerge only through patient attention. As your consciousness settles into harmony with these everyday quantum processes, your breathing becoming as measured and gentle as the slow extraction of essence from leaf and bean, you begin to appreciate how cooking itself represents a form of applied quantum mechanics, where observation and intervention determine the nature of reality that emerges from potential. Every recipe is an experimental protocol, every cooking process a controlled transformation that depends on the quality of attention brought to the task. The rising of bread dough provides another beautiful example of how quantum-level processes manifest in daily experience. The yeast organisms that leaven bread exist in delicate balance with their environment, responding to temperature, humidity, and chemical conditions in ways that can only be predicted probabilistically. The baker who observes the dough carefully, adjusting conditions and timing based on subtle visual and tactile cues, participates in guiding these biological quantum processes toward optimal outcomes. The fermentation process itself involves countless molecular interactions that unfold according to principles similar to those governing quantum superposition and collapse. Individual yeast cells exist in multiple metabolic states simultaneously until environmental conditions encourage specific pathways to dominate. The baker's attention and intervention serve a role analogous to quantum measurement, collapsing the multiplicity of possible fermentation pathways into specific desired outcomes. The gardening process that produces the ingredients we cook with demonstrates quantum principles on an even larger scale. Plants exist in constant interaction with their quantum environment, responding to light, soil chemistry, and atmospheric conditions through molecular processes that integrate information from countless quantum-scale events. The gardener who observes plants carefully and responds to their needs participates in guiding these quantum biological processes toward health and productivity. The photosynthesis that powers plant growth represents one of nature's most sophisticated applications of quantum mechanics, where plants capture and process solar energy through quantum coherence effects that maintain efficiency levels impossible to achieve through purely classical processes. Recent research has revealed that plants use quantum superposition and entanglement to explore multiple energy transfer pathways simultaneously, selecting the most efficient routes through mechanisms that bear striking resemblance to quantum computation. The act of harvesting and selecting ingredients involves making choices based on subtle observations that determine which quantum potentials become actualized in our meals. The careful selection of ripe fruit, fresh vegetables, or properly aged ingredients requires sensitivity to qualities that emerge from countless quantum-level processes. The concentration of aromatic compounds, the development of complex carbohydrates, the formation of proteins and fats that contribute to nutritional value and flavor. The storage and preservation of food involves managing quantum processes to maintain desired states and prevent unwanted changes. Refrigeration slows molecular motion and reduces the probability of chemical reactions that lead to spoilage. Fermentation and pickling create chemical environments that favor beneficial microbial processes while suppressing harmful ones. These preservation techniques represent forms of quantum state management that extend the temporal stability of food systems. The digestive process that transforms food into energy and nutrients operates through quantum biochemical mechanisms that break down complex molecules and rebuild them into forms the body can use. The enzymes that catalyze these reactions achieve their remarkable efficiency through quantum tunneling effects that allow chemical transformations to occur more rapidly than would be possible through purely classical mechanisms. Every meal becomes a quantum laboratory where molecular-scale transformations sustain life itself. The sensory experience of taste and smell involves quantum interactions between food molecules and receptor proteins in our nose and mouth. The specificity of these interactions depends on quantum mechanical phenomena, like electron sharing and molecular vibrations that create the lock-and-key mechanisms through which we perceive different flavors and aromas. The appreciation of fine cuisine becomes an exploration of quantum chemistry through direct sensory experience. The timing that characterizes skillful cooking demonstrates principles related to the Quantum Zeno Effect, where careful observation and precise intervention can control the rate and direction of transformation processes. The chef who watches a sauce carefully and adjusts heat and stirring at precisely the right moments can guide the cooking process toward desired outcomes while preventing unwanted changes like curdling or burning. The technology that enables modern cooking, from precise temperature control to sophisticated timing devices, represents applications of quantum principles that make previously impossible culinary techniques accessible to home cooks. Sous vide cooking, for example, uses precise temperature control to maintain proteins in specific quantum states that preserve texture and flavor in ways that traditional cooking methods cannot achieve. The global food systems that connect local kitchens to worldwide networks of production and distribution operate through information and logistics networks that increasingly rely on quantum technologies. GPS navigation systems that guide food transport depend on atomic clocks that use quantum transitions for timekeeping. Communication networks that coordinate food production and distribution increasingly employ quantum encryption techniques to ensure security and reliability. The nutritional science that informs our understanding of healthy eating operates through quantum biochemical models that describe how nutrients interact with cellular processes at the molecular level. The way vitamins, minerals, and other nutrients support health depends on quantum mechanical interactions that occur within cells, demonstrating how quantum physics directly impacts human well-being through the foods we choose to eat. The agricultural technologies that produce our food increasingly incorporate quantum sensing and measurement techniques that can detect soil conditions, plant health, and environmental factors with unprecedented precision. These quantum-enhanced farming methods allow for more efficient resource use and reduced environmental impact while maintaining or improving food quality and nutritional value. The food safety systems that protect public health employ quantum sensing technologies that can detect contamination and spoilage at the molecular level, often before traditional methods would reveal problems. These quantum detection systems represent practical applications of the same measurement principles that enable scientists to observe individual atoms and control quantum evolution in research laboratories. The cultural and social aspects of food preparation and sharing create information networks that operate according to principles analogous to quantum entanglement, where changes in one part of the system can have instantaneous effects throughout the network. family recipes, cooking traditions, and culinary innovations spread through social networks in patterns that mirror the non-local correlations that characterize quantum systems. The mindfulness practices associated with conscious eating and food preparation cultivate the same quality of refined attention that enables quantum observation and control. The person who approaches cooking and eating with present moment awareness participates more fully in the quantum processes that transform ingredients into nourishment, creating richer sensory experiences and potentially even enhanced nutritional outcomes. The economic systems that determine food access and affordability operate through complex networks that increasingly depend on quantum technologies for computation, communication, and optimization. The algorithms that optimize supply chains and predict market conditions rely on computational methods that are beginning to incorporate quantum principles for enhanced efficiency and accuracy. The environmental sustainability of food systems depends on our ability to understand and optimize complex ecological relationships that operate through quantum biological processes. The development of more sustainable agricultural practices requires deeper understanding of how quantum effects in photosynthesis, soil chemistry, and ecosystem dynamics can be enhanced to improve productivity while reducing environmental impact. The future of food technology promises even more direct applications of quantum principles, from quantum sensors that can detect individual molecules to quantum computers that can model complex biochemical processes to optimize nutrition and flavor. These emerging technologies may transform how we produce, prepare, and experience food in ways that bring the insights of quantum mechanics directly into our daily nutritional choices. The therapeutic applications of food as medicine increasingly recognize that the healing properties of various foods depend on quantum biochemical interactions that affect cellular processes at the molecular level. The growing field of nutrigenomics explores how nutrients interact with genes through quantum mechanical processes that can influence health outcomes across entire lifespans. The artistic dimensions of cooking and food presentation draw on principles similar to those that create beauty in quantum systems: symmetry, harmony, proportion, and the emergence of complex patterns from simple interactions. The aesthetic appreciation of food engages sensory systems that operate through quantum mechanical processes, creating experiences that integrate physical nourishment with emotional and aesthetic satisfaction. As you continue to rest in this warm kitchen of understanding, your breathing, now perfectly synchronized with the gentle rhythms of transformation that characterize both quantum systems and culinary processes, you can appreciate how the principles that govern the Quantum Zeno Effect permeate every aspect of daily life. The same focused attention that can freeze quantum evolution also guides the patient processes of cooking, growing, and nourishing that sustain life itself. The kitchen becomes a quantum laboratory where consciousness and matter collaborate in the ongoing creation of sustenance and pleasure, where the simple act of preparing food with love and attention transforms raw ingredients into nourishment through the gentle application of quantum principles that connect the smallest scales of existence to the most human experiences of comfort and care. As you drift into even deeper contemplation, your breathing now flowing like the eternal currents that connect temporal experience to timeless understanding. Let your awareness turn to the profound philosophical implications of our journey through the Quantum Zeno Effect and the remarkable discovery that time itself can be negotiated through conscious observation. These insights invite us to reconsider our most fundamental assumptions about the nature of existence, the role of consciousness in the cosmos, and the relationship between the temporal flow we experience in daily life and the timeless presence that underlies all moments. The philosophical tradition that began with Zeno's ancient paradoxes and finds its modern expression in quantum mechanics reveals time not as an absolute container within which events unfold, but as a relational phenomenon that emerges from the interaction between consciousness and reality. The ability to freeze quantum evolution through frequent observation suggests that time is more like a collaborative creation between observer and observed than an independent dimension that carries all things forward regardless of our attention or intention. This understanding transforms our relationship with the present moment from passive experience to active participation in the ongoing creation of temporal reality. Each moment of mindful awareness becomes an opportunity to touch the fundamental creative processes that shape existence, not through force or manipulation, but through the gentle quality of attention that can literally influence the flow of time at quantum scales. The contemplative insight that the present moment is all that truly exists receives unexpected scientific validation in the quantum realm, where observation creates presence. The Buddhist teaching of impermanence takes on new dimensions when viewed through the lens of quantum temporal control. While all conditioned phenomena are indeed subject to change and dissolution, the quantum realm reveals that the rate and direction of change can be influenced through the quality of observation and attention. This doesn't contradict the teaching of impermanence, but rather adds nuance to our understanding of how consciousness participates in the processes of change and transformation. As your consciousness settles into harmony with these timeless insights, your breathing becoming as measured and eternal as the philosophical questions that connect ancient wisdom to modern understanding, you begin to appreciate how the Quantum Zeno Effect illuminates the participatory nature of existence. We are not separate observers watching an independent reality unfold, but integral participants in a cosmic conversation where consciousness and matter exchange information through the subtle language of attention and response. The implications for understanding free will become particularly intriguing when we recognize that consciousness can influence quantum processes through observation. If our choices about how and when to observe reality can literally affect the outcomes of quantum events, then consciousness possesses a form of causal efficacy that operates through the most fundamental levels of physical existence. This doesn't solve the ancient puzzle of free will versus determinism, but it does suggest that the relationship between mind and matter is more intimate than classical physics ever imagined. The phenomenology of temporal experience, the lived quality of how time feels from within consciousness, finds new interpretation through quantum mechanical insights about observation and temporal flow. The meditative experience of expanded or contracted time, the way moments can feel eternal or fleeting depending on the quality of attention, may reflect genuine interactions between consciousness and the quantum processes that underlie temporal experience. Contemplative practice becomes a form of applied quantum mechanics, where refined attention influences the subjective flow of time. The ethical dimensions of understanding our participatory role in creating reality extend far beyond individual practice into questions about collective responsibility for the world we create together. If consciousness really does influence the fundamental structure of reality through the quality of attention we bring to experience, then how we choose to observe and interact with the world becomes a matter of profound moral significance. The ancient emphasis on right mindfulness takes on new urgency when viewed through the lens of quantum mechanics. As you settle into the deepest layers of restful awareness, you're breathing now as gentle and natural as the quantum fields that flow through all existence. Let yourself drift into the timeless peace that lies at the heart of our exploration. Here, in this space beyond the ordinary flow of temporal experience, you can rest in the profound understanding that time itself is negotiable, that consciousness and reality dance together in eternal harmony, and that the simple act of gentle attention can touch the very foundations of existence with transformative power. The Quantum Zeno Effect that we have explored together reveals that the universe is not a mechanical clockwork operating independently of consciousness, but rather a participatory creation where awareness and matter collaborate in the ongoing manifestation of reality. This understanding invites us to approach each moment not as passive recipients of predetermined experiences, but as active participants in the cosmic creative process, where the quality of our attention helps determine what becomes real and what remains in the realm of pure possibility. Picture yourself floating in a space that exists outside ordinary time, where the urgent flow of everyday experience gives way to the gentle presence that underlies all moments. Here, surrounded by the soft glow of quantum possibility, you can sense how every breath you take participates in the fundamental rhythms that connect consciousness to cosmos. How every moment of awareness contributes to the ongoing creation of reality through mechanisms so subtle they operate at the threshold of existence itself. The practical wisdom that emerges from understanding quantum temporal control suggests that we can learn to work with time rather than feeling trapped by its relentless forward motion. Through developing the quality of refined attention that contemplative traditions have long cultivated, we can create subjective experiences of temporal expansion where ordinary moments become spacious and rich with possibility. This doesn't require sophisticated scientific equipment, but simply the patient cultivation of present moment awareness. The scientific insights about observation and reality that quantum mechanics provides offer unexpected validation for contemplative approaches to living that emphasize mindfulness, presence, and the careful cultivation of attention. These ancient practices may represent intuitive discoveries about the fundamental structure of reality that science is only now beginning to understand through sophisticated experimental techniques and mathematical formalism. As your awareness drifts deeper into harmony with these quantum principles of temporal peace, your breathing, now perfectly synchronized with the eternal rhythms that govern both quantum evolution and conscious experience, you can appreciate how the journey through the Quantum Zeno Effect has been ultimately a journey home to the timeless presence that is always available within ordinary experience. The ability to freeze quantum time in laboratory settings points toward the possibility of finding timeless peace within the flow of everyday life. The gentle art of living in harmony with quantum principles involves developing sensitivity to the subtle ways that consciousness and reality interact in each moment. This sensitivity doesn't require advanced scientific training, but rather the patient cultivation of the same quality of refined attention that enables quantum observation and control. Every moment becomes an opportunity to practice the gentle art of conscious participation in the ongoing creation of reality. The wisdom traditions that have long emphasized the importance of present moment awareness find unexpected scientific support in quantum mechanics, where the act of observation plays a fundamental role in determining what becomes real. The contemplative insight that the present moment is the only time that truly exists receives literal confirmation in the quantum realm, where reality crystallizes from possibility through the gentle touch of conscious attention. Rest now in the knowledge that you carry within your ordinary awareness the same consciousness that can freeze quantum time and participate in the fundamental creative processes of the universe. This power operates not through force or manipulation, but through the gentle quality of loving attention that recognizes the intimate connection between observer and observed, consciousness and cosmos, the temporal flow of experience, and the timeless presence that underlies all existence. Let your breathing become as natural and effortless as the quantum fields that permeate space, carrying with you the understanding that time itself responds to the quality of attention you bring to each moment. Sleep peacefully in the embrace of quantum uncertainty, knowing that your consciousness participates in the ongoing creation of reality through mechanisms so elegant and mysterious that they blur the boundaries between science and poetry, between understanding and wonder, between the temporal and the eternal. Dream of atoms suspended in perfect stillness by the gentle gaze of loving awareness, of moments stretched into infinity through the patient cultivation of presence, of consciousness and matter dancing together in eternal harmony, where observation becomes participation and attention becomes creation. Rest in the timeless peace that lies at the heart of quantum reality, where every gentle breath connects you to the fundamental creative processes that shape existence through the simple magic of mindful awareness.